So what happens if we have an equilibrium system and we dilute it, or we change its pressure? Well, first of all, we're going to look at changing pressure. We're going to look at the gaseous example. So what I've got is I've got a container here containing a mixture of gases A, B and C. So I've got a lid on my container there. I've got gas A floating around in here, gas B floating around in here, and some gas C particles floating around in here. And so what I did, I've got this mixture, I've got gases A, B and C all at equilibrium. There is no net reaction occurring in this system here. The gases are at equilibrium. And what I then did was I took the lid of my container and I pushed the lid down. I reduced the volume of my container. So I've still got gases A, B and C inside my container. So I've just got these very roughly drawn particles here. But I've still got gases A, B and C inside my container. So what have I done here? I've decreased the volume. And in doing that, seeing as we've still got the same gases inside my container, I haven't taken any gases out, I have also therefore increased the pressure. So the Chatelier's principle states that an equilibrium system will partially oppose any change applied to it. So the change I've applied here is the increased pressure. So that means the system itself will decrease pressure. How can a system decrease its own pressure? Well, it can decrease its pressure if it can find a way to reduce the number of particles in the container. If the system can react in such a way so as to reduce the number of particles in this container, then if we have less particles within this volume, we're going to have less pressure. How does the system reduce the number of particles? Well, let's look at the chemical equation. On the reactant side, we have 3 particles, and on the product side, we only have 2 particles. So that means if the system wants to counter the increase in pressure, if the system wants to decrease its pressure, it wants to undergo a forward reaction. If we increase the pressure, if we decrease the volume of our container and therefore increase the pressure, then the gases in the mixture will undergo a net forward reaction, thereby reducing the number of particles in the container and then opposing this increase and causing a decrease in pressure. So a forward reaction here will cause a reduction in the number of particles and therefore a reduction in the pressure. Alternatively, if we'd increased the volume and decreased the pressure, then the system would have re-increased the pressure by in fact undergoing a net back reaction, and then until it reached a new equilibrium in this new volume. So basically, as I change the pressure and I change the volume of a container containing these 3 gases, the number of mole of each of the gases at the point of equilibrium changes. We have a different equilibrium forming in different sized containers. That's what's going on here. Now, if by chance we in fact had the same number of particles on either side, let's say we've only got 1 molecule of gas B here, and therefore we only had 2 particles on the reactant side of our equation, then no matter how we change the pressure or the size of our container, the equilibrium system would not be altered by it, because if we increase the pressure of our container, there's no way, no matter if the gases go in a forward reaction or a backwards reaction, the system can't change the number of particles. Both the forward and back reaction neither produce nor get rid of any particles. We have the same number of particles on both sides of the equation, so that means the system itself cannot try and counter any change in pressure. If we have the same number of particles here and here, then nothing happens to the equilibrium when we change the pressure of our container. So changing the volume of a gaseous mixture is one way to change its pressure. However, there is one other way that we need to consider. So let's go back to our original equation and our original container. So we can increase the pressure by reducing the volume of the container, but we can also increase the pressure. We'll just fix this up. We can also increase the pressure by adding an inert gas. If we take some inert gas and pump it into the container, into the container that's holding gases A, B and C, then we are going to increase the pressure inside the container. I've still changed this back to a 2. This should read a 3 here. So we've pumped inert gas into the container, and that has caused an increase in pressure. However, this increase in pressure is not going to cause any equilibrium changing, because although we've pumped the inert gas in, the partial pressures, that is, the pressure in the container exerted by gases A, B, and C, the partial pressures of gases A, B, and C are unchanged. Their own pressures are unchanged. So although there is an increase in the pressure inside the container, the partial pressures, or the pressures exerted by just the gases A, B, and C, remain the same. And what that means is that there will be no net effect on the equilibrium of this mixture. If we'd increased the pressure by reducing the volume, then we would have seen a net forward reaction as the gases try to decrease the pressure. However, because this pressure increases because of the inert gas, we see no equilibrium shift because this addition of the inert gas has not changed the partial pressures of A, B, and C. So there is no equilibrium shift in this case. So that is how we can analyze the changing pressures or the changing volumes of a gaseous mixture. And adding an inert gas has no effect on the equilibrium, but changing the volume of a gaseous mixture changes the pressure and therefore causes an equilibrium shift. Now, if we wanted to analyze a dilution situation, then we could do almost the exact same thing. So if we get rid of these states, if we change these states and we look at a solution, an aqueous solution, we can analyze it in the exact same way. So if we have a beaker here containing some sort of solution, and I add more water to this solution and I dilute it. Well, if I'm diluting water, I am increasing. So I'm increasing the volume. And if we're thinking about the gaseous example, this translates to a decrease in pressure. However, here we're not dealing with a gas, we're dealing with a solution. So rather than a decrease in pressure, we're dealing with a decrease in the concentration of all our particles. Not just the concentration of any one substance, just the general concentration of particles of A, B, or C in this mixture. So keep in mind these are all aqueous now. So we've seen a general decrease in the concentration of particles in our solution. So according to this principle here, the system will oppose this change and try and increase the concentration. How does it increase the concentration of particles? Well, it undergoes a net back reaction because the back reaction will produce more particles, therefore increasing the concentration of particles in our solution. So diluting a solution or increasing the volume of an aqueous solution is exactly can be analyzed in exactly the same way as if we increased the volume of a gaseous mixture. In both cases, we would see a net back reaction for this reaction here in order to produce more particles and increase the pressure or increase the concentration of particles in our solution. Now, another consideration that's very important, although in a lot of cases, if we have a different number of particles on the reactant side and the product side, we will see a net forward or net back reaction as a result of a change in volume. It's also important to realize that when we dilute or when we increase the volume of a gaseous mixture, there's also, as well as the net reaction that occurs as a result of that occurs in order to allow this equilibrium shift to occur, there's also an immediate change to the concentrations of individual gases. Or gases or substances. So if we dilute this, then there will immediately be a drop in concentrations of all of A, B, and C, and then following that immediate drop in concentrations, we will see the effects of the equilibrium shift. So we're going to go through an example of how we can do this. So we're going to take a look at a gaseous example, and we're going to draw a concentration versus time graph for this example. So what we're going to be looking at is the changing in volume of a mixture of two gases, and these gases are N2O4, which is being used to produce NO2. So this is the mixture of gases that we are dealing with. Now we're going to say that we have a container containing these two gases at equilibrium, and what happened is that the volume was reduced to 1/3 of the original volume. So maybe we started with 1 litre, with a 1 litre container containing these two gases at equilibrium, and we've reduced the size of that container to 1/3 of a litre. So what I'm going to do is I'm going to try and figure out how to draw a concentration versus time graph. So we've got concentration on the vertical axis and time on the horizontal axis. So initially we've got concentrations of N2O4 and concentration of NO2 listed on our axis, on our vertical axis. So these are the abstract numbers at which the initial concentrations are. Let's just say that they start here. Now if the volume is reduced to 1/3 of the original volume, then that means we're going to see an immediate spike, an immediate tripling in the concentrations of these two gases. If the volume is reduced to 1/3 of its original volume, then we're going to see an immediate jump in the concentration to triple the initial value. So we're going to see a jump to triple the initial value. The same for our N2O4. So the concentrations of both of these gases is immediately tripled due to the decrease in volume. Now, because we've decreased the volume, we have increased pressure, and so the system of gases counters this increase in pressure by undergoing a net back reaction, producing one particle and using up two particles. So a net back reaction here is reducing the number of particles and therefore reducing the pressure. So that means a net back reaction will mean a drop in concentration of NO2. So that will look like this. And we'll also have an increase in the concentration of N2O4, and that increase will be half the size of the decrease in NO2 because we have a 2 here and a 1 here. So we see an increase in the concentration of N2O4 like so, and we know that the size of this increase is equal to exactly half the size of this decrease. So that's how we analyze the changing in pressure or the dilution of a system at equilibrium. Basically, the system adapts and either increases the number of particles or decreases the number of particles. However, if the forward reaction and the back reaction both produce the same number of particles, for example, if this was in fact 2 particles on the reactant side of the equation and 2 particles on the product side of the equation, then there would be then diluting or changing the pressure of a system would have no effect on the equilibrium. There would be no net reaction.